Okay, this video is to help you with number 2, 3, and 12 and 13 on your Kinematics horizontal kinematic sheet. There's a lot of common questions here, so I just wanted to address them through the video. And then that way I can answer everybody at the same time, and if you have any further questions, feel free to ask. So here's a concept that they want you to know here. First of all, you have a plane that you've already found out was slowing down. It started off with 70 meters per second going north. That's directional. 70 meters per second is your magnitude, and north would be your direction. Okay? And so just be aware of that. Now, it's slowing down, so we know that the acceleration is working against the velocity. Remember, if acceleration and velocity are working together, that means you're speeding up. So if I have a positive velocity and a positive acceleration, I'm speeding up. And same is true if I have a negative acceleration. If I have a negative velocity and a negative, acceleration, let me do it down here. If I have a negative velocity and I have a negative acceleration, I'm speeding up because they're both working together in the negative direction. And you could call positive right, you could call it west or east, it just all depends on what direction you're calling positive. But whenever your velocity and your acceleration are in opposite directions, that's when you slow down. No matter which you do, as long as they're opposite, you're going to be slowing down. And so that's the concept here. So magnitude is basically how fast, and direction is, positive, negative, right, left, north, south, east, west. Okay, so whenever they ask for magnitude on a vector arrow, the length is your magnitude, and the direction of the arrow is the direction. So I would have two arrows right here, and they're the exact same magnitude, but opposite directions. So if they were a force, like a push, two people pushing against each other, since the magnitudes are the same, they are going to be the same. However, let me just change the color of this one. If the green arrow happened to be larger, then, and this was two people pushing on each other, the length of the arrow would mean that that person had more force than the red. So then, in this case, they would win and the object would end up going this way. So the length of the arrow is magnitude, or how strong, and the direction it's pointed is, of course, the direction. So let's go ahead and look at this next one here. So that being said, let's look at the problem. It says on the diagram below, and let me use another color, point P represents the position of the jet on the runway. Okay, we do know the jet is heading north, right? Because the problem said he was going 70 meters per second north. Okay, and it wants to know the magnitude and direction of the acceleration. We already know the acceleration. The acceleration was given right here, 2 meters per second squared. So it's given right here. So I'm just going to pull that down. Okay, and so this is 2 meters per second squared. All right, now here's what we have to be careful of. If we're calling north positive, then that means south would be negative. So technically that acceleration would be negative. All right, and we know it has to be working south because it's slowing it down. If I'm going north and I'm slowing down, my acceleration or my brakes or whatever it is that is the force working against the direction of motion has to work in the opposite direction. So because of that, we're going to draw an arrow downward from P, okay? Because velocity is up, but acceleration is going to be in the opposite direction. Now, they want you to draw this to scale, and they're saying 1 centimeter equals 0.5 meters per second squared. So if I need to get 2 centimeters, the magnitude is the 2, all right? And the direction is the negative. And so what we're going to do now is just draw that arrow. So if I have to have a magnitude of 2 and each centimeter is 0.5, it would take 4 centimeters. So I'd take my ruler and I would draw a line that was 4 centimeters long, pointing south, and that would be the direction of acceleration, the magnitude and direction of acceleration. And of course, that would equal 2 meters per second squared south. Okay, and so again, we're drawing an arrow just to get you used to that, or to remind you of the fact that you are dealing with vectors and they are directional. Length is magnitude, and then wherever the arrow is pointed would be the direction that's being directed in, that acceleration. So, all right, now let's move on to number 3. Number 3 is not difficult, but it is different than what you're used to. If I had this worded without the data table, you would think it was an easy problem. So now we just got to look and figure out what this data table is saying. It says an observer recorded the following data for the motion of a car undergoing constant acceleration. So here's what we got. We got time. We have an initial time, and we have a final time. And here we got speed, but we're going to call this velocity. We have some initial velocity and we have some final velocity. So they're giving me a change in time here, and they're giving me a change in velocity there. All right, so they want me to calculate acceleration. So what I'm going to do now is go to my formulas and say, okay, do I have any formulas with time and velocity, initial and final, to solve for? And that would be kinematic number 1. Final velocity equals initial velocity plus AT. And if you rearrange that, this is that equation we first started with. Acceleration is a change in velocity over, it's really a change in time. And remember, we normally don't have to subtract time, but this is one of those cases that we do. It's really a change in velocity over a change in time, but normally time is given, but in this case, you don't start at time 0. And so you'll just plug in your numbers. So your final, so I'll come down here. Final velocity is going to be 8.5 meters per second minus my initial, which is 4 meters per second. And then my time, my final time is 6 seconds minus 3 seconds. So that means a total of 3 seconds went by. And so when you do your math, you're going to get 1.5 meters per second squared. Now again, don't just circle it and go. You need to put it in the calculator, because on a test, you have to be able to make sure you're putting it in the calculator correctly and getting the right answer. All right, so lastly, let's try 12 and 13. This ticker right here, there's a video that I put online, just like a 4 or 5 minute video that discusses this ticker tape problem. And then I want you to watch that before you try it. Some of you guys may have already attempted it, but you still need to watch the video, because I'll keep track of who's all doing those and probably do a homework grade of all those. All right, so here's what we got. It says a physics class is to design an experiment to determine the acceleration of a student on on inclined skates coasting straight down a gentle incline. The incline has a constant slope. The students have a tape measure, traffic cones, and stopwatches. So produce a procedure. I'm going to sketch the procedure over here. We're not really talking about number 17, but I just need more room to do that. And so let's just kind of give a layout. So here's the ground, and we've got this slight incline that goes all the way down. And so you got to think, I can get time, right? And I have a tape measure, so I can get distance. So tape measure is going to be a delta X measurement. Stopwatch is going to be a T measurement. So, and they want me to calculate the acceleration of the incline, determine the acceleration down the incline. So I'm going to start looking at my formulas with acceleration, and all 3 of them have it. But I need one with time, okay? And I also need one with distance. So if you look at kinematic equation number 2, and you say, okay, I have x equals x final equals x initial plus initial velocity t plus 1/2 gt squared, or at, I'm sorry, we're not in vertical yet, at squared, and then you got v squared equals the initial squared plus 2a delta x. Now the problem with this equation right here is we don't have final velocity. We don't know what speed that person's going to reach, so we can't use that one. So we eliminated the first one We eliminate because it has time, but it does not have position, and we eliminated this one because it doesn't have time, but it has position, but we don't know final velocity. So this is the equation that we're going to have to use. So what we could do is take one of the cones and set it up, take the tape measure and measure another cone somewhere down here, and we can call this x initial equals 0, and we can measure how far we put it, and this would be x final here. Then we could time it, the time it takes to get all the way down. That'll be my change in time. Okay, and we know we can just make sure that he starts with an initial velocity of 0. So we know that. And if we look down here at equation, we know this, we know this, we know this is 0. We can find our time, and we're solving for acceleration. So in words here, you would just say place 2 cones a set distance and that could be any distance within reason. It's got to be on the ramp. A set distance apart. Then we could time how long it takes to travel the distance of the cones. All right, and so that's a way of looking at this. Now, you may find another way of doing it, and you feel free to share that with me and see what you come up with. Okay, so that's that. So then, of course, indicate the equation that we would use. You almost have to do that as you're filling it out, and we would, of course, use x final equals x initial, which is a position, remember. Initial velocity times time plus 1/2 at squared. And that's going to be our formula. So you could easily solve that in a lab setting. Okay, I hope that helps. If you have any further questions, feel free to ask.